Should we use a 4-core cable or a single-core cable in the project? In this section, I want to talk to you about cable selection. About when to use a 2-core cable. When a 3-core cable makes sense. And when multi-core cables are the right choice. We'll go through how to calculate voltage drop. And everything that can turn cable selection into a real challenge on a project. When you choose a cable for a project, different conditions lead to different cross-section values. If you stay with me until the end, you'll clearly see which cable cross-section is the correct choice for your project. So, stay with me till the end. A film crew wants to shoot at a location. They have several floodlights. Every time they turn them on, their equipment suffers from voltage drop. So they ask us to run a separate cable from the main distribution board to prevent voltage drop issues with their equipment. Now the question is it better to use a multi-core cable or a 2-core cable? The distance from the main distribution board to the floodlight location is approximately 300 meters, and the total power of the floodlights is 18 kilowatts. Alright, first of all, let's go to the formula. In the first step, we use the allowable voltage drop method. This formula is used for long cable runs, where the voltage drops along the length of the path. The formula is as follows. The formula is as follows. 2 times the cable length multiplied by the power in watts. Then we divide the result by the constant number 56. Multiply by the allowable voltage drop of the cable, which is 5%. And finally multiply by the system voltage. And the number 2 means that we have 2 current paths. The outgoing path and the return path, phase and neutral. 56 is the electrical conductivity factor of copper. If our cable were aluminum, we would use 36 instead. First, we calculate the cable size. If we use a 2-core, single-phase cable, which means 220 volts, the distance is 300 meters. The power is 18 kilowatts, which is 18,000 watts. 5% voltage drop of 220 volts equals 11 volts. And our system voltage is 220 volts. After calculating all these values, we reach the number 80. According to international standards, there is no cable with this exact cross-section. So we choose the next higher standard size, which is 95 square millimeters. Now, if we use 3-phase power instead of single-phase power, how does the cable cross-section change? To make it economically beneficial for us. So, let's calculate it together. That is, instead of powering all the projectors from a single-phase supply, we divide the total load of the projectors among the 3 available phases. The cross-section formula in the 3-phase case is as follows. We multiply the cable length by the power. Then divide the result by the constant number 56. Multiply by the allowable voltage drop of the cable. And multiply by the system voltage. Here, the number 2 is no longer used. Because in a 3-phase system, the go and return path is not defined in the same way as in single-phase systems. Alright. Now let's calculate what the cable cross-section should be. If we use a multi-core, 3-phase cable, which means 380 volts, the distance is 300 meters. The power is 18 kilowatts, which equals 18,000 watts. 5% voltage drop of 380 volts is 19 volts. And our system voltage is 380 volts. After calculating these values, we reach the number 13. According to international standards, there is no cable with this exact cross-section. So we choose the next higher standard size, which is 16 square millimeters. Method for calculating the allowable voltage drop in a 3-phase system when the current is known. Now, let's talk about the formula. Using a real, practical example. The distance between the load and the main panel is 400 meters. The current required by the loads is about 80 amperes. The allowable voltage variation is 12 volts. And the power factor is considered to be 8/10. Now, let me explain why I considered the voltage variation to be 12 volts. According to existing standards, from the transformer to the main panel, or the electricity meter, the maximum allowable voltage drop is 5%. 5% of 400 volts equals 20 volts. So, we subtract this 20 volts from the 400 volts available at the transformer. And the voltage at the main panel becomes 380 volts. From the main panel to lighting loads, the allowable voltage drop is 3%. 3% of 380 volts equals 12 volts. We then subtract this 12 volts from 380 volts. And the voltage at the equipment terminals becomes 368 volts. For non-lighting loads, the allowable voltage drop from the main panel is 5%. However, since in most cases, we do not clearly know what type of loads we are dealing with, it is safer and more conservative to assume a 3% voltage drop from the main panel to the load. The voltage drop occurs from the transformer to the main panel, and from the main panel to the project location. Keep in mind, these voltage drops apply when the distance between the equipment is long. If the distances are short, the voltage drop is negligible. That's why the cable calculation formula changes in two different situations. I'll explain this to you using several practical examples. As we know, our loads draw 80 amperes. And we want to use a multi-core cable installed in free air. So, according to the table, We select a 16 square millimeter cable. In the next part, we will go through this table, using more examples, and also cover other factors that you need to consider. Now, if in a project we do not have the load current, we need to refer to the required power of the project. In this case, the formula takes a different form, and I want to explain the cable cross-section calculation based on power more clearly using an example. So stay with me. We want to calculate the required cable cross-section for a 150 kilowatt electric motor with a power factor of 8/10, and the distance between the motor and the main distribution board is 30 meters. Before calculating the cable cross-section, we must note that the power written on the motor nameplate is mechanical power, and it needs to be converted into electrical power. To do this, you simply need to look at the table. Whatever the motor power is, divide it by the motor efficiency, shown in the table, to obtain the electrical power of the motor. In our example, the motor power is 150 kilowatts. According to the table, we divide this value by the motor efficiency, which is 93%, to obtain the electrical power. Now, if in a project we do not have the load current, we need to refer to the required power of the project. In this case, the formula takes a different form, and I want to explain the cable cross-section calculation based on power more clearly using an example. So stay with me. We want to calculate the required cable cross-section for a 150 kilowatt electric motor with a power factor of 8/10, and the distance between the motor and the main distribution board is 30 meters. Here, we obtained the cable cross-section using the allowable voltage drop method. Now let's compare it with the result we get if we use the allowable current method based on the tables. Then we'll see which cable size should actually be used, and which choice would be wrong. To calculate the cable cross-section using the allowable voltage drop method, we need the project current, not the power. So, using the following formula, the first step is to calculate the current. Now that the current is known, let's move on to the cable cross-section tables. So stay with me. Our current was 274 amperes. If we look in the section for multi-core cables, and the part related to installation in free air, we find the closest current value to 274, which is 285 amperes. This current rating corresponds to a cable with a cross-section of 120 square millimeters. Now let me tell you an important point. These current ratings and cable cross-sections, for example, 285 amperes for a 120 square millimeter cable, are based on an ambient temperature of about 30 to 35 degrees. If the ambient temperature changes, whether the cable is installed in free air or in the ground, we need to apply a correction factor. What this correction factor is and how it works, I'll tell you right now. Our electric motor is installed in an environment where, in summer, the ambient temperature reaches 45 degrees. So the correction factor becomes 79 hundredths. We multiply 285 amperes by 79 hundredths, which gives us 225 amperes. That means, at a temperature of 45 degrees, a 120 square millimeter cable can carry only 225 amperes. So we must select a cable with a larger cross-section to solve this problem. For example, if you refer to the table, a 185 square millimeter cable is rated for 370 amperes. Now we calculate again. 370 multiplied by 79 hundredths equals 292 amperes. This value is sufficient for our load, which is the electric motor. The mistake many people make is ignoring the cable correction factor. As a result, they choose the wrong cable and later are forced to replace it, which carries a high economic cost. This method is called the allowable current method. We calculated the cable cross-section using two different methods. As you can see, the allowable voltage drop method does not give a correct result for short distances, because a 25 square millimeter cable is not suitable for a current of 274 amperes. So, for short distances, we must use the allowable current method, which means referring to the standard tables. If the ambient temperature where the cable is installed is usually between 30 and 35 degrees Celsius, according to the tables we use a 3-core, 120 square millimeter cable. But if the temperature reaches 45 degrees Celsius, a correction factor must be applied. In that case, the appropriate cable cross-section for our project becomes 185 square millimeters. Stay with me in the next sections, where we'll explore more important topics together.